So let's now think about linear regression in matrix form. We know that the equation for a single one-dimensional line is given just by y equals mx plus c. But in general, there can be higher dimensionality to the data than just a single point for x. In fact, there could be multiple points for x. And then we'd have an equation of the form y equals m1x1 plus m2x2 and so on plus c. Now we can write this in a more compact form where x is actually in a matrix and w is in a matrix, but we still have to add on the weight term, but we can get around that by actually expanding out the expression and then considering what it actually means to get rid of the WC. How can we pack WC into the weight matrix? What do we have to do with x? Well, we kind of did this before, so we can now say, let's rewrite it now such that we've got x hat w hat, but what we've done is we've appended a 1 on the end of data vector x, and we've appended the WC onto weight vector w. Right. So in other words, what we've done is we've just kept all the current versions, current values of x. We've appended it with a 1 at the end here, and we've appended the weight matrix with a WC here. So when we multiply the last term, it basically just adds on the constant term, right? So we've managed to rewrite that in this appended form, which is nice and clean, so we haven't got any odd terms on their own, and it makes analysis a lot easier. So if we had 10 one-dimensional data points, this is just an example of what the data is going to look like after we've appended it. We then append the data, so we've still got 10 rows of data, right? We've still got 10 rows of data and 2 columns now. The first data point is actually going to be, the first column now is going to be the data point that it was. So as we go down here, these are the different samples, right, on the different rows, and in the first column we've just got the x value corresponding to that sample, and then what we've done is we've appended in the second column, we've appended a 1. Correspondingly, we change the size of the weight matrix in this particular simple case. If we have y equals mx plus c, the one-dimensional case, then we've obviously got the first value now in our weight matrix is going to be the m, and the second one is appended with the c. In this particular case, what we see is that if we've got this data set 10 by 2 for the data vector and 2 by 1 for the weight vector, then the overall size of the output is going to be 10 by 1. We can immediately look at the dimensionalities of the data and of the weight matrix. 10 by 2 multiplied by 2 by 1 means we're going to end up with 10 by 1 values of y in this case, right? So in this particular example, we're just having a single output and a single x value and a single threshold value, but we've packed them together in the weight matrix. And that's what the output looks like. So we've got 10 values, so each value here, in each row here corresponds to each of these input values coming in on x. So we can define the vector error now in terms of the difference between the measured y values and the predicted y values. So the error is going to be basically the values for y that we've got, take away the predicted values, and that's going to be x times w, where w is obviously the weight vector. So we can define the sum of the squares then. Let's remember now that E is a vector by actually multiplying E transpose by E. So what this is going to do is it's going to multiply each element in the error vector with itself and then add them all together. So that's exactly what we want it to do. We want the sum of the squares. So we can expand this expression for sum of squares SSE, E transpose E. Let's just substitute in the error. So we've got y minus xw transpose times y minus xw. And this is just indicating the dimensionalities we've actually got in this particular example we looked at before. In this particular example, the y would be a 10 by 1, the x would be a 10 by 2 because we've got m and we've got c, and the the x would be a 10 by 2, so we've got the data values, and for each sample we've got the data value and also the constant term of 1, and the w is going to be 2 by 1, so basically it's going to have, the first element is going to be what we had for m before, and the second one's going to be for c, and the result will be 10 by 1. Okay, and we see that the SSE is going to be 1 by 10 multiplied by 10 by 1, so that'll be a single value. So like I said, what we're doing is we're multiplying each error element with itself and add them all up, so we end up with one value. So given we've got this sum of squared error terms, what we can do is we can now rearrange the first expression. So we've got y minus xw and the whole thing's transposed. Since we know what to do with transposes, we know that AB transposed equals the same as B transpose times A transpose, and we did that in when we were looking back at the vectorized operations earlier. We can immediately write the first term then slightly differently. So the y goes to y transpose, and the xw goes to w transpose x transpose, right? So we've taken, basically we're doing the transpose now inside the bracket rather than outside the bracket. So now we've got to multiply out this expression. So as you can see, it's going to be y transpose times y, take away y transposed times xw, that's this term. Then it's going to be minus w transpose x transpose times y, minus w transpose x transpose times y, that's this expression here. And then the last one's going to be, there's two negatives, it's going to be plus w transpose x transpose x w, w transpose x transpose x w. Okay, so we have this expression for the sum of the squared errors. First of all, we notice actually the size of this. Well, first of all, we notice that this thing is going to be a 1 by 1, right? We already said that this is a 1 by 1, so we're multiplying y transpose by 1, so we end up with a single value for this. So this is also going to be a single value, and this is going to be a single value. In fact, you can go through if you wish and have a look and just check what the actual values and the sizes of these things are. The first term, y transpose, is going to be a 1 by 10 matrix, x is going to be a 10 by 2, w is going to be a 2 by 1. Right, so go through yourself and check that those are the case. And if we see multiplying all of these things together, we notice first of all that the adjacent dimensions are the same, so we can multiply that, and we can multiply that and that. And the external, or so I should say the outside dimensions are 1 by 1, so we end up with a 1 by 1 value. And the same thing is true here. If you look through it, we end up with a 1 by 1 value. So consequently, these are 1 by 1 values. And if it's a 1 by 1, it means we can transpose it and the value's the same. So we notice first of all that these central terms are scalars. So using again this basically operation that we can take the transpose of a product and we switch the order of the matrices and then we individually transpose them. What we can see is we can look at this term, the first term here, y transpose x w, and we can transpose it, and we end up with, basically we switch the x and the w round, we transpose both of those, and the y transpose just goes to a y. So that's substituting in, if you like, a and b as being the corresponding parts here, and you can see in this particular case the b corresponds to the xw and the a corresponds to y prime, y transpose. We can just substitute that in, and we see that the transpose of the first term here equals this term here, but this term here is actually the term we've got here. So in other words, this term here, the first term and the second term, are actually transposes of each other, but it's only a 1 by 1, right? Because it's a 1 by 1, they're the same value. Therefore, basically, we can just add both of them together. Right, so we can, because they're transposes of each other, we can transpose one of them and it's equal to what it was before, and then we just, rather than having these two terms, we have two lots of one of these terms, and we can choose which one it is we got. So what we're going to do is just going to choose the 2 y transpose xw. Okay, so we've now rewritten SSE in a slightly more compact version. We've just basically combined these two terms together. Now what we want is a closed solution to specify what the sum squared error is. And in order to do that, of course, all we have to do is we have to differentiate the expression with respect to the weight vector and see when it goes to 0. Right? That's what we're going to do, because we're interested in finding the weights. Right? That's why we have to differentiate with respect to the weight vector. So we've got our expression that we just derived, and what we want to calculate now is the derivative of this error with respect to the weight vector, because what we need to do is we want to know all the values in the weight matrix, or the weight vector. So we calculate ddw of our expression. So let's just do them one at a time. First of all, let's notice that y transpose y, if we take the derivative of that with respect to w, goes to 0 because there are no terms of w in there, right? The second term, derivative with respect to w of minus 2 y prime x w, or we can let's just slightly rewrite it. We take out the minus 2 first of all, and then we want the derivative of, in this case, y transpose x times w. And what we can see is we can use the formula for derivative with respect to w. We notice when we have the form xw, then basically the derivative with respect to w goes to x transpose, right? So looking at this, the derivative we want and the formula, we see the y transpose x corresponds to the x, right? So therefore, we can basically look at this and say, well, in that case, the y transpose x term, when we take the derivative, we end up with that being the result, but we have to transpose it, right? So basically the w disappears, and we end up the transpose of this first term in brackets. And we can also again say, well, let's take out the transpose. Let's take the transpose inside the brackets again. So all we have to do is switch the order and transpose each matrix. So we end up with x transpose y. So we end up with a nice simple expression. We put the minus 2 back in front of it, and we end up with the expression here, ddw of minus 2 y transpose xw equals minus 2 x transpose y. Now we've got one more term to sort out, which is the quadratic term, if you like. So now we're going to look at the inner term, and we're going to say, well, x transpose x, let's write that as a matrix, because again, then we can actually write it in a form that we can use the formulas we derived earlier to actually deal with. We notice, first of all, x transpose x is going to be a symmetrical matrix. Okay. Second thing we notice is we can rewrite the w transpose x w. We can switch out the x transpose x term in the middle and put in a, like we've just done above here, because we've put in this substitution. And then we've got this derivative with respect to w transpose a w. And we know what the answer to that is, because again we derived that. And in the case where a is symmetrical, and it is symmetrical because a is just x transpose x, what we see is we end up with 2aw. Okay. So now we've got this expression. We can then substitute the x transpose x back in again. So we end up with derivative with respect to w transpose x w equals 2 x transpose x w. So we've got all our values now. So we've got our derivative is therefore given by minus 2 x transpose y plus 2 x transpose x w. Now, we want to find the solution to that in order to find the minimum, right? And we want to find the w, which gives us the minimum, don't forget. So we set this expression to 0. And then we can slightly rearrange it. First of all, we can we can divide by 2, and then we can move this negative term onto the onto the right hand side. So we end up with x transpose x w equals x transpose y. Now if this was just a simple scalar equation, you just divide each side by the factor in front of w, but we can't do that because generally speaking it's going to be a matrix. So what we do is we multiply each side by the inverse of x transpose x, because then we have x transpose x inverse times x transpose x w equals, and then the same on the other side, x transpose x inverse times x transpose y. And we know the first term here, the inverse times, well, basically a matrix multiplied by its inverse is going to be the identity matrix, so we can actually ignore it. Therefore we end up with the expression for w, which equals x transpose x inverse multiplied by x transpose y. And we can also, of course, then predict the y values as well. So this is one result that we want. We can also predict y equals xw. So all we have to do is now say x hat now is our x values multiplied. In fact, that shouldn't really be a hat there, should it? It's going to be our x values multiplied by x transpose x inverse times x transpose y, and then we can basically calculate some predicted values using this expression. So I mentioned it earlier, but we'll just say one more time. Computing then the vectorized parameters in Matlab is a very easy thing to do. First of all, we put the data in appended matrices, so don't forget we've got to account for the last value being a 1. So we've got our x value vector transpose times x vector, take the inverse, then it's the x vector transpose multiplied by the y output vector, and that will just directly give us the weight matrix. And it's totally trivial to run that kind of calculation in Matlab. You just say inv to get the inverse of a matrix, x transpose multiplied by x, that'll do the multiplication, the little tiny apostrophe does the transpose, multiplied by x transpose y. And that single line will do the linear regression in Matlab for us. And this is just pointing out again w. Now in the single dimension case, w would contain m and c in the column vector, and x contains augmented input data, and y is going to be the output column vector, right? So don't forget we can also use the regress function as well, but it's kind of nice to do things from first principles so you can have an understanding of where it all comes from.